Hi, I'm happy to share with you my BH project, FPGA-accelerated agent-based simulation for COVID-19. COVID-19 is a highly contagious disease that transmits mainly via droplets. Decision support systems that enable healthcare professionals to predict and contain the spread of the epidemic are in great need. Among modern artificial intelligence techniques, a useful approach to build such decision support system is agent-based modeling. Agent-based modeling is widely used as an AI approach to analyze stochastic and chaotic systems. Given the agent setup and their action in each time step, the simulation procedure updates the agent's states through time. During the simulation, the algorithm keeps track of each agent for further analysis. Such simulation can become very computationally demanding, especially for large models that capture complex interaction between agents. There is a great need for hardware acceleration. This project proposes an FPGA-based accelerator for agent-based epidemic modeling for COVID-19. The key idea is to decouple the on-chip resource from the population size to enable partial calculation. In this way, a chunk processing routine could be implemented to optimize throughput for the kernel design. An algorithmic adaptation has also been proposed to reduce latency caused by conditional branches within loops and decrease the delay path. We have also managed to reduce data transfer time with shared virtual memory mapping. An experimental implementation on Intel Arria 10 FPGA achieves 2.3 times speedup over 10 Intel Xeon CPU cores. It is also twice as fast as an Nvidia GeForce GPU. An parametric performance model has also been proposed for resource estimation. In general, there are two approaches to accelerate the simulation of agent-based epidemic modeling using FPGA. One approach is to accelerate the simulation of a well-tested model in a straightforward manner. Each agent in the population will occupy dedicated on-chip resources. However, the on-chip resource usage grows quickly with the population size. When the population requires more resources than the device can offer, it will be impossible to simulate the model. Our proposed design avoids this problem by decoupling the correlation between the resource usage and population size. Another approach is to adapt the model to facilitate hardware acceleration. However, the simulation can become less reliable and the model can become difficult to calibrate. Our proposed design also avoids this problem by adopting a well-studied epidemic model with public domain software. To try to enjoy the benefits of both approaches while avoiding their disadvantages, this project mainly wants to present one possibility: accelerate a well-tested model in software with novel computational routine designed for hardware. Our software reference is Covidim, a micro-simulation model developed by the MRC Center of Global Infectious Disease Analysis hosted at Imperial College London. Covidim models the transmission dynamics and severity of COVID-19 through a spatially and socially structured population over time, which also takes into account intervention policies and healthcare situations. Through this research, there are many 5 challenges. The first one is to decouple the on-chip resource from the population size, as previously mentioned. The second one is to optimize throughput for the kernel design. The third one is to reduce hardware latency caused by complex control flow. And the fourth one is to reduce data transfer time. Finally, we want to propose a parametric model for resource estimation. We propose one solution for each of the challenge: a preprocessing routine for partial calculation, a chunk processing and buffer system, some control flow conversion, implement stereo virtual memory mapping, and finally, we could optimize a customizable simulation model. So let me briefly go through each of the solutions. The first one is to decouple the on-chip resource usage from population size. We need to propose a processing routine for partial calculation. The key insight is that we can propose a computational routine on the host program to transform the memory access pattern from random to sequential. The basic steps includes reorganizing person records, add paddings to each cluster, which means household in this context, and then we can flatten them to device-compatible data structures. The computational routine on the host program would only take ON times and ON additional spaces with a small constant, and it will only increase off-chip memory usage and normally be activated only once of each simulation procedure. We have also counted the percentage of the pre-processing computational routine compared to the whole simulation program. It has been proven that it will take only around 10% of the execution time, which means it will not increase the computational complexity dramatically. The parameter arrays are divided into independent chunks. Each chunk can then be buffered and processed separately to minimize communications between on-chip and off-chip memories. Fixed size parameters such as age group susceptibility are stored in global parameter buffer. Before processing each chunk, relevant parameters are first parsed and stored in individual status buffer. In this way, the calculation no longer needs direct access to off-chip memory. The result buffer is activated when all calculations are finished for an individual, and the results will be stored in the off-chip memory after all individuals of a chunk are processed. A compile-time kernel resource usage estimation tool has been used to quantify the benefit we could get through the buffer system. As a result, throughput is almost inversely proportional to the bottleneck resource usage. We could see that with the proposed buffer system, the throughput is almost double. Another challenge that limits performance is the latency caused by control flows. As the simulation procedure includes frequent status checks, there are lots of nested conditional branches within loops. These branches can cause difficulty for static optimization and exhaust on-chip resources. An algorithmic adaptation is therefore proposed to mitigate this effect and reduce latency and delay paths. Instead of justifying whether an individual should be infected, the target for each simulation procedure is directed to calculate the probability for one individual to be infected. The force of infection is used as a basis for final probability. Most conditional branches within loop are thus converted to arithmetic operations that measure the impact on the resulting probability. The fourth solution we provided is shared virtual memory optimization. Previously, in order to do the data transfer, we need to allocate the memory objects and buffer on the host and device address space, and then we need to copy the data from the host memory to the device buffers. And now, with the shared virtual memory address space, which is directly accessible from the device, we could just allocate SVM buffers on the address space and then map the address of SVM buffer to host address space. In this way, we could directly write data to SVM buffers on the host program and then access them on the device. If we divide the whole execution flow into those four parts, and then we call the write data from host to device and from device to host the data transfer time, and then we could see that it takes almost around 15% of the total running time. Thus, with the SVM optimization, it could be estimated that we could save most of the data transfer time. We compile and run the hardware design using FPGA-accelerated platform on the Intel Dev Cloud. It can be seen that the current resource bottleneck for FPGA implementation is the ALUTs. It's within our expectation because of the nature of the agent-based simulation. We have also evaluated and compared the execution time of one simulation procedure on the CPU and the GPU platform. The population size in the experiments ranges from 10 million to 500 million. The implementation on the FPGA platform achieves about 2.3 times speedup against the 10-core CPU and up to 2 times speedup against the GPU implementation. Then we can estimate the number of Arria 10 FPGAs needed to simulation one timestamp in 1 second, given that each FPGA has enough on-chip memory to support accurate calculation, and the host program can update the parameters for all FPGAs in parallel. Finally, it comes to our fifth solution, which is that we can provide a customizable simulation model for the parametric resource estimation. It can be generalized from the model that there are 4 main components when propagating newly infected cases, as shown below. Then we can basically adapt our data structures to generalize the number of affecting factors of each component to a variable n. We have compiled this more generalized design on a bigger hardware called Stratix 10. We have found the bottleneck resource are RAMs and FFs. Assuming there are 10 affecting factors for each component, we could see that we can achieve around 35 times speedup compared to a single core CPU execution on Intel Xeon Gold CPU. Through a further kernel area analysis, we can see our bottleneck area are place factor evaluation and suspectability calculation. As those two parts are almost fully enrolled on the kernel, the resulting throughput is almost directly proportional to the outermost enroll factor. In this way, the upper bound of throughput for a device could be estimated through this formula. As it takes little modification to support other simulation like fluke, one possible direction for future work is to see how it could work for other ABMs. The second one is to do buffer effective analysis. Although there is no cache hierarchy on the FPGA chip, we could still do some analytical analysis on the buffer system. Another direction is to provide effective support for epidemiologists. One major step to do this is to migrate to AWS or Azure, which could support more complex host program compilation. Also, since the simulation time depends on the throughput, we mainly optimize the throughput for the proposed design. A direction of future work is that to optimize other aspects, such as power and energy efficiency. In conclusion, the project presents an approach to speed up the household FOI evaluation in the Covidim microsimulation model. There are 4 main source level optimizations for the hardware architecture, which includes preprocessing for partial calculation, data buffering, control flow adaptation, and shared virtual memory mapping. An implementation of the proposed accelerator on an Intel Arria 10 FPGA achieves 2.3 speedup over 10 Intel Xeon CPU cores. It is also twice as fast as an Nvidia GeForce GPU. Since FPGA are becoming available in cloud computing systems such as Azure and AWS, it is our hope that this work will start a new direction contributing to the acceleration of general ABMs and fighting against epidemics.